We're always trying to find a better way to do things. But what if there was a perfect way? The absolute best, most efficient, most effective method you could possibly find? Well, it's not just a thought experiment, there's a whole science dedicated to it. So today, we're going to pull back the curtain on the science of best. Okay, so think about this for a second. Imagine you're developing a new medicine. Good enough isn't going to cut it, right? You need the most effective formula, the safest process, the fastest production. The stakes are, quite literally, life and death. So how on earth do scientists find that one perfect solution? All right, here's our game plan. We'll kick things off with the old trial and error way of doing things, then we'll define what optimization really is. After that, we'll map out all the possibilities, explore 2 different strategies to get the best outcome, peek inside the toolbox of methods, and then wrap it all up with the big picture. For, centuries, the way we've made progress has relied on experimentation. But the classic approach, well, it's got a pretty big flaw. The traditional method, right, is you take a process, you change one single thing, and you see what happens. Did it get better? Great. Did it get worse? Okay, go back. It sounds logical, but it's incredibly slow. And what's worse, you might totally miss how different factors work together to create an amazing result. It's kind of like trying to solve a maze by only ever turning right. You might get there, but you probably won't. So, if the old way is just stumbling around in a maze, there has to be a better way. And lucky for us, there is. It's a concept called optimization, and it is a total game changer. The word itself pretty much says it all. To make perfect. Optimization isn't about guesswork or just hoping for the best. It's a formal, structured process for finding the absolute best way to use the resources you already have, taking into account all the little things that can affect your final outcome. And this is why it's so important. Optimization is not just some academic exercise. In a field like medicine, sure, it saves money and time, but critically, it also improves safety by cutting down on errors. And it's what drives the innovation that leads to better and better treatments. So how do you actually do optimization? Well, it starts with understanding what you're working with. You have to break the problem down into 2 key parts. First up, you've got your independent variables. Think of these as all the knobs you can turn. The ingredients you put in a formula, the temperature of a reaction, how long you mix it for. They're the things you control. And then you have the dependent variables. This is your results, the effectiveness of the drug, how stable it is, how quickly it dissolves. It depends on the settings of all those knobs you just turned. And this is where it all comes together visually. When you map the relationship between all those variables, you get something called a response surface. The best way to think about it is like a 3D map of a mountain range. Your inputs, the knobs you can turn, are the coordinates on the ground. And the height of the mountain at any point, that's your result. So what's the goal? To find the very highest peak on that map, because that peak is your perfect, optimal outcome. Now, finding that peak isn't a one-size-fits-all kind of deal. There are actually 2 fundamental philosophies for how to climb that mountain and find the summit. These strategies really boil down to 2 core ideas. The first is to optimize as you go. This is like climbing the mountain by taking one step, checking your altitude, and then deciding where to step next based on what you just learned. It's really cautious and it's adaptable. The second is to plan up front. This is more like sending out a bunch of scouts to map the entire mountain range first. Only when you have the complete math do you plot a direct course to the highest peak. It's super comprehensive, but it takes a lot more work right at the start. Okay, so each of these strategies has its own set of tools. Let's dive a little deeper into that first strategy, optimize as you go, and look at one specific tool for the job. One of the classic methods here is called evolutionary operations, or EVOP. In this quote, it just nails the whole idea. You're not making big, risky changes. Instead, you allow the process to gradually, slowly evolve toward perfection through small, really carefully planned adjustments. So here's how it works in practice. First, you make a tiny, almost unnoticeable tweak to your process. Then, and this is key, you repeat this new process many, many times. Because the change is so small, you need a lot of data to see if it had any real effect. Then, you use statistics to see if that tiny change actually led to an improvement. And if it did, awesome. You lock it in and you make another small change in that same successful direction. It's a slow, steady, and really safe climb to the top. The trade-off? It's incredibly reliable, but it can take a very, very long time to reach that peak. So,
Let's step back from the specific tools for a second and look at the entire game plan. How does all this come together in a real-world project?
As you can see from this plan, true optimization is a highly structured journey. It's not random at all. You start with a clear goal, you identify all your variables, the knobs you can turn, and the results you're going to measure, and then you design your experiments to build that mountain map we were just talking about. You use math to find the peak on that map, and finally, you test and verify your results before you roll it out. It is a rigorous, scientific method for turning an idea into its best possible self.
And that's really the key takeaway here. Optimization isn't some kind of magic. It's a powerful and systematic engine for progress. It's the hidden science that takes a process from just good enough to the absolute best it can be, whether you're creating a life-saving drug or just trying to perfect your morning coffee.
It really makes you think, doesn't it? This whole framework for finding the best way can be applied to so much more than just a lab. So I'll leave you with this question. What in your world is just sitting there, waiting for its perfect solution?